Dear students, in this video we are going to study about Fleming's right hand rule and also about the motional EMF from Lorentz force. Now let us study about Fleming's right hand rule. When a conductor moves in a magnetic field, the direction of motion of the conductor, the field, and the induced current are given by Fleming's right hand rule, as given in this figure. So here the direction of the field is shown. The direction of current is also shown in this direction. Therefore, this conductor will move in direction given by this right hand thumb rule. The thumb, index finger, and middle finger of right hand are stretched out in mutually perpendicular directions as shown in the figure. If the index finger points in the direction of the magnetic field and thumb indicates the direction of motion of the conductor, then the middle finger will indicate the direction of the induced current. This Fleming's rule is also known as generator rule. Next, we will study about the motional EMF from Lorentz force. For this, let us consider a straight conductor which is in the shape of a rod AB of length L in a uniform magnetic field B, and that is directed perpendicularly into the plane of the paper as shown in this figure, shown by this cross. The length of a rod is normal to the magnetic field, and let us consider that the rod moves with a constant velocity v towards right side as shown in this figure. When the rod moves, the free electrons present in it also move with the same velocity v in B. As a result, the Lorentz force acts on the free electrons in the direction from B to A and is given by the relation Fb equals minus E times V cross B. The action of this Lorentz force is to accumulate the free electrons at the end A. So here the electrons will get accumulated. This accumulation of free electrons produces a potential difference across the rod, which in turn establishes an electric field E directed along BA, as shown here. So the electric field E is created, and this is considered to be having a positive charge, and here at this end there is a negative charge. Because of this potential difference, there will be an EMF induced in this conductor. Therefore, this accumulation of free electrons will produce a potential difference across the rod, and that will establish an electric field E which is directed along BA. Due to this electric field E, the Coulomb force starts acting on the free electrons along AB and is given by this relation Fe equal to minus E times E. This magnitude of electric field E is that will keep on increasing as long as the accumulation of electrons at the end A continues. And the force Fe also increases until equilibrium is reached. And at equilibrium, what happens? The magnetic Lorentz force Fb and the Coulomb force Fe balance each other, and there will be no further accumulation of free electrons at the end A that will be taking place. Therefore, Fb equal to Fe, and here this expression can be written as minus E times V cross B equal to minus E times E, and this expression can be written as Vb sin 90 equal to V. As the sin 90 is equal to 1, Vb can be written as the electric field E. The potential difference between two ends of the rod is given by V equal to V times L. So V can be written as Vb L. Thus, the Lorentz force on the free electrons is responsible to maintain this potential difference and hence produces an EMF given by the expression E equal to BLV. As this EMF is produced due to the movement of the rod, it is often called as motional EMF. And if the ends A and B are connected by an external circuit of total resistance R, then the current is given by I equal to E by R, that's equal to BLV by R. That will flow through the conductor. The direction of its current is found from right hand thumb.
I am John Ambrose Fleming. The thumb, index finger, and middle finger of right hand are stretched out in mutually perpendicular directions. If the index finger points the direction of the magnetic field and the thumb indicates the direction of motion of the conductor, then the middle finger will indicate the direction of the induced current.